So today we're going to discuss types of relation. Now, a relation in set A is a subset of A cross A. Now, I told you yesterday that we can have a relation between elements of two different sets, but it is also possible to get a relation between elements of the same set. So suppose I say set is given by set of boys Raj, Rahul and Ram. So we have a set of boys like this. So there are two types of sets basically. One is empty set and the other one is universal set. Now what is empty set? From the very empty set or empty relation. So empty relation basically means that if no element of A is related to any element of A. So it means that Raj is not related to Rahul, Raj is not related to Ram, Rahul is not related to Ram. So no element of set A is related to any element of that same set. So let me just give you an example of such a relation. Suppose I say A comma B, element of A cross A, that is the Cartesian product. A is a sister of B. Now here you see, if you pick any one of the three, you can never get one of them is a sister of the other one. So this relation, that sister relation, is not possible at all. So here we see that it is known as empty relation. So A is a sister of B. This one will be a null set because there is no such element related to other element of that same set A. Now universal relation. Universal relation means that each element of A is related to every element of that same set. So I say, you first of all think of what is the Cartesian product. The Cartesian product is nothing but Raj, comma, we have here Raj, then we have Raj, comma, Rahul, then we have Raj, comma, Ram. Like this way it will go on. Then we have Rahul, comma, Raj, then Rahul, comma, Ram, then Rahul, comma, Rahul, Ram, comma, Raj, Ram, comma, Rahul, then Ram, comma, Ram. So like this way, that's the Cartesian product, and that is what the universal relation is also. So every single element is related to everyone in every element of that set A. So that is what universal relation. So you see here that R is equal to A cross A. So the relation R is the Cartesian product of that same set. So if each element of A is related to every element of A, that is R is equal to A cross A, is known as the universal relation. So if I have to give you an example, so example will be that A comma B, A and B studies in the same school. Yes, you see Raj comma here, Raj comma Raj is an ordered pair. Yes, they study in the same school. He's the same person, he's studying in the same school. Raj comma Rahul, Raj and Rahul goes to the same school, so they're studying in the same school. It's like that. Okay, so this is a universal relation. So when I have a set, suppose I define a set 3 boys of Don Bosco Junior School, so they're all studying in the same school. So if I have to form ordered pairs, those of you who are studying in the same school, so every 2 of them which I pick, they are studying in the same school. So that is the universal relation. Each element of A is related to every element of A. Clear? So that's what empty relation and universal relation is all about. Now the last line you see here, what it's written is that both empty relation and universal relation are sometimes called trivial relation. Now what do you mean by trivial relation? So basically it goes like this. Suppose you have to, suppose you are asked to count the number of students in a class. Okay, now think of the class is totally empty. The class is totally empty, so it's quite easier to count. So you can directly, by looking at the class empty, you can directly say the number of students is 0 without even doing anything, no hard work, you just directly say 0. Now again, if the class is totally full, if the class is totally full and you already know the total number of students in that class is 60. Now the class is totally full, so you don't have to count, you don't have to do anything. You can directly say that the class has 60 students in it, right? Now if some of them are absent, then you have to go to the register, you have to check the attendance and all, then you have to count and all. It will be total hard work. So there are two cases in which you don't have to do anything, you can easily tell the answer. One is when the class is empty, and the other one is when the class is totally full. So those two conditions which are easily found are known as trivial. So here empty relation, you can easily get the answer, that is the null set, and universal relation also you can easily get the answer, that is nothing but the Cartesian product, that is nothing but the Cartesian product of the set. So since these two things you can easily find, that's why these two relations are known as trivial relations. Okay, so there we have types of relation. Now we have equivalence relation. So what do you mean by equivalence relation? Now for any relations to be equivalence relation, it needs to follow three different criteria. One is it has to be reflexive, then it has to be symmetric, and it has to be transitive. Then only we can call them as equivalence relation. Now when can a relation be reflexive? So here I said we have done what? Relation, that universal relation we have done. What was that? Ram comma Ram, then Raj comma Raj, Raj comma Rahul, and all. We went on like this, right? So reflexive, a relation can be reflexive when A comma A is an element of R. Here you see Ram comma Ram is there, right? So A comma A is an element of R, then we can say that the relation is reflexive. Suppose I have a set A, that is A comma B. Now when our relation, if I define a relation like this, A comma A, then B comma B. If I define a relation like this, where each element is related to itself, now this relation will be reflexive, okay, where A is related to A itself. So reflexive. Let me just give you an example. So L1 comma L1 is an element of R, and what is that R? R stands for A is parallel to B. Now every line is parallel to itself. We know that every line is parallel to itself. How can two lines be parallel? When their slopes are equal. And you see that if I say that this line L1 makes an angle theta with the x-axis, then it's the same line. So it again makes the theta angle with the x-axis. So it's what? The slope is equal. Now since the slope is equal, the line is parallel to itself. So you see here L1 comma L1 satisfy the relation, that is parallel to A is parallel to B, satisfies this relation. So L1 comma L1 is an element of R. Hence this relation becomes reflexive. Okay. So here an example is given. R is equal to what? 1 comma 1, 2 comma 2, 3 comma 3. So this is an example of reflexive relation. Now when can a relation be symmetric? Now for symmetric, same here. If I have A is equal to A comma B, now if a relation we have as A comma B and B comma A, if these two are there, so A comma B is there and B comma A is there, then we can tell this relation to be symmetric. So if A1 comma A2 is an element of R, implies that here it will be A2 comma A1, A2 comma A1 is an element of R for all A1, A2 element of A, then we can say it is symmetric. So I told you that suppose my A is A comma B. So for this relation to be reflexive, we have, if in the relation I have A comma B, in the relation I have A comma B, then B comma A also must be there to be reflexive. So here A1 comma A2 is an element of R, implies that A2 comma A1 is an element of R. A comma B is there and B comma A is there, and for all A1 A2, for all A1 not A1 A2, it will be for A and B, for all A and B element of what? Element of this capital A, because the relation in that set A, right? So we have this symmetric relation. So what can be an example? So suppose I say that there are two lines, line L1 and line L2. Now when I write L1 comma L2, what does this mean? It's just the same relation, A is parallel to B. So L1 comma L2 means what? Line 1 is parallel to line 2. Line 1 is parallel to line 2. That's why it becomes element of that relation. Now in the same way we can say that line 2 is parallel to line 1. If these two are parallel, we can say in opposite way also that line 2 is parallel to line 1, right? So L2 comma L1 is also an element of R. Hence this one becomes symmetric. Hence the relation A is parallel to B is also symmetric. Okay, so example here we have 1 comma 2 comma 2 comma 1. Okay, so that's how we get symmetric. Now what is transitive? Transitive is, suppose in here we have to have three elements. Suppose we have a set A comma B comma C. Now for a relation to be transitive, suppose A comma B is there, then B comma C is there. So for this relation to be transitive, A comma C must be there, then we can say it to be transitive. So here it says if A1 comma A2 is an element of R, A2 comma A3 is an element of R, you see A comma B, B comma C, then implies that then if A comma C is also present in the relation, then we can say the relation to be transitive. A comma B, B comma C, these two have to be present. First I have to check whether these two present or not. If they are present, then I will check whether A comma C is there. Then A comma C is there, then we can say the relation to be transitive. Okay, so here suppose I have three lines. I told you here three elements are there, A, B, C. Suppose I have three lines in here, line 1, line 2, line 3, line 1, line 2, line 3. Now if I say the first two condition was what? A comma B, I told you what? A comma B must be an element of R. Suppose I say line 1 is parallel to line 2. I'm saying that line 1 is parallel to line 2. Okay, sorry, suppose I'm saying line 1 is parallel to line 2, then I am saying that line 2 is parallel to line 3. This line 1 is parallel to line 2 and line 2 is parallel to line 3. Now combining these two, can I say that this line 1 is parallel to line 3? I can say that, right? This line 1 is parallel to line 3. So I can write line 1 is parallel to line 3 because line 1 parallel to line 2, so their slopes are equal. Now line 2 parallel to line 3, their slopes are equal. So we can get what? Line 1 and line 3, their slopes are also equal, right? So we have line 1 and line 3 to be parallel. So since they are parallel, we can say this relation to be transitive. So what we can say is that A is parallel to B, the relation is reflexive, symmetric and transitive all at the same time, and that's why it is called an equivalence relation. You see here L1 comma L2 element of R, L2 comma L3 element of R. So both of them implies L1 comma L3 element of R. So here is an example, 1 comma 2 is there, you see A comma B is there, then 2 comma 3 is there, B comma C is there, and we have A comma C in here. Okay, so relation is transitive. Now here is an example of equivalence relation is given. A relation R in a set A is said to be equivalence relation if R is reflexive, symmetric and transitive, which I already told you before. An example R is given, 1 1 is there, 2 2 is there, 3 3 is there, 1 2 look at here, this 1 1 2 2 3 3 makes it a reflexive. Now here I haven't mentioned the set A. The set A must be 1 2 3. This must be the set A, elements of set A. So this 3 makes the relation reflexive. Now 1 2 is there, 2 1 is there. So these two makes the relation to be symmetric, right? 1 2 is there, 2 1 is there, symmetric. A comma B, B comma A, symmetric. Now for transitive, what I'm going to do? Now look at here, 1 comma 2 is here. Let's write 1 comma 2 is here. Then 2 comma 3 is there. Then 2 comma 3 is there. So I have these two. After looking at these two, what I will check? Whether my 1 comma 3 is there or not. And yes, 1 comma 3 is there. So we have this relation to be transitive. Okay. But if you look carefully, this relation is not equivalence relation. Why it's not equivalence relation? Because you see here 2 comma 3 is here, right? But 3 comma 2 is not here. 1 comma 3 is here, right? But 3 comma 1 is not here. So for this relation to be equivalence relation, these two also must present in this relation, then only it can be equivalence relation. Okay, so that's how it goes.